So the last thing we did was Gaussian surface and its properties.
No, I got it. I got it. We did Gauss's theorem, then Gaussian surface and properties we did. Next
Okay.
study, derive expression for electric field intensity near charged sphere. When we say charged sphere, there are three possibilities. It can be hollow. One minute. Hollow, conducting / non-conducting, and solid conducting. That means in all cases charge will come on the surface. Right heading?
Yes.
Yes. 1 minute on one paper I am sending to one group, then we are starting. Derive expression for electric field near charged sphere. It can be hollow conducting, non-conducting, and solid conducting. This is a sphere. With center O, radius R. So consider a sphere to be charged uniformly with positive charge Q, center O, radius R. With the help of Gauss's theorem, we have to find what is electric field intensity. So for Gaussian surface, we have to consider the symmetrical surface such that it will pass through point where we want field. So this is point P. Consider sphere with center O, radius R to be charged uniformly with positive charge Q. P be a point at a distance R from center O near the sphere. Draw a Gaussian sphere with center O, radius R. It will pass through point P. Intensity at point P is directed normally outward, correct? No?
Yes.
Because it charge is positive, normally outward, since it is radius. Radially outward is normally outward. Let ds bar be the small area surrounding point E. Draw diagram now. Current?
Yes, sir.
Any doubt?
No.
and just write a part completing this. We'll stick to the planner which I give. Huh?
Yes, sir.
If you stick to that, Nasi, by October end, entire syllabus will get over, and then only revision. You can try for good colleges and admission.
Yes. Yes, sir.
Okay. Draw Gaussian sphere with center O, comma, radius R. It will pass through point P. The intensity E bar at point P is directed normally outwards. Let ds bar be elemental area surrounding point P. Therefore, by Gauss's theorem, phi is q upon epsilon naught, q inside upon epsilon naught, which is E bar dot ds bar over pure surface. Now copy till this. Monday onwards, then we can start with our regular time, 7 o'clock. Or you want 8 o'clock only? Which time, beta?
And with 7.
7. Okay.
Yes, sir.
Q inside that Gaussian sphere is Q only upon epsilon naught. E is constant, so bring outside into ds cos 0 because they are in same line. What is integration of di for the Gaussian surface? It is 4 pi r square. Hello?
Yes, sir.
So E will become 1 upon 4 pi epsilon naught q by r square. This is expression for electric field near charged sphere. Copy.
Yes.
Okay. Case 1. Point lies on the surface. If point is on the surface, then distance becomes radius, correct? E will become 1 upon 4 pi epsilon q by r square. Case 2. Point lies inside the sphere. That means r is less than r. What will be charge enclosed now by Gaussian sphere? Can you tell? See, this is main sphere. At distance r, if you draw Gaussian sphere, charge is on the outer surface. What will be charge enclosed by this Gaussian sphere? Zero.
R,
Zero, no, charge is outside where it can enclose.
right.
So E will become 1 upon 4 pi epsilon naught 0 by r square. That means E is 0. So intensity at any point inside charge sphere is always 0. Right, case 1, case 2.
Yes.
Graph of E versus R for charged sphere. Say nothing given means it is hollow sphere. If point is inside, that means at center, what will be R? 0, no? Hello?
Yes.
Till R becomes radius, there is no intensity. As soon as it becomes radius, E becomes maximum, which is 1 upon 4 pi epsilon naught q by r square. And then inversely proportional to r square. Clear? Graph clear?
Yes.
Right.
Yes.
So if sigma is surface charge density, then sigma is charge upon that area 4 pi r square. So wherever you see q, you can write 4 pi r square. So E will become 1 upon 4 pi epsilon naught. Q is 4 pi capital R square upon small r square. 4 pi cancel. So E will become sigma into R square upon epsilon naught R square. Write as a note. Done?
Yes.
Yes.
Okay. Derive expression for electric field intensity for solid non-conducting sphere. Solid non-conducting means charge will be inside, it won't come outside. So consider a solid non-conducting sphere with center O, radius capital R, having volume charge density rho. That means it is charge per unit volume. So first part we'll take outside, then on the surface, then inside. Let P be a point. Again, see. Is having charge inside as rho per unit volume. O is center, R is radius, and P is a point. At a distance R near this charge conducting non-conducting sphere. Draw a Gaussian sphere B with center or radius R. It will pass through point P. Intensity at point P is directed normally outward. ds bar be the elemental area surrounding point P. By Gauss's law, charge inside upon epsilon naught is integral of E bar dot ds bar. What will be charge inside? It is rho into 4 by 3 pi r cube. Correct? See, charge is situated inside this sphere. So rho into 4 by 3 pi r cube. Correct?
Yes.
But we are taking full sphere, this Gaussian sphere. Gaussian sphere's volume will be small r cube. So don't make that mistake. This is E ds cos 0. So rho into 4 by 3 pi r cube E into ds cos 0 is 1. Rho into 4 by 3 pi r cube E into Gaussian area is 4 pi r square. So 4 pi cancel, r square r cancel. So E becomes rho r upon epsilon 0 I didn't wrote. Upon epsilon naught upon epsilon naught. Upon epsilon naught. This is the formula. Okay. First case followed. Point is outside wala. Hello.
Yes.
Okay. Copy this much. Draw diagram. Then I will tell that consider wala part. Then complete. Right. Consider a solid non conducting sphere having positive charge of volume density rho. Volume density means charge per unit volume. Let P be a point. Let P be a point at a distance small r. Let P be a point at a distance small r from center O. Let P be a point at distance small r from center O near charged sphere. Draw a Gaussian sphere B with center O, radius small r. It will pass through point P. Let E bar be field at point P. Let ds bar be elemental area surrounding P. Therefore, by Gauss's theorem, flux phi equals to done.
Yes.
Okay. Case 2. Point lies on surface. Then same, small r is capital R. So E will become rho into capital R upon epsilon naught. Case 3. Important one. Point lies inside. See, this time charge is not on the surface. Charge is inside. These are the charges throughout. Sphere of radius capital R. So if I consider a point P inside and draw Gaussian sphere with center or radius r, then this much charge it will enclose. Correct?
Yes.
So can we say by Gauss's theorem, Q inside upon epsilon naught will be E area ds of the Gaussian surface. Q inside is rho into volume of inside is 4 by 3 pi r cube. Hello?
Yes.
Equals to E into 4 pi r square. So this 4 pi 4 pi will get cancelled. R square, R will get cancelled. So we get E equals to rho R upon 3 epsilon naught. Copy. See, first one I made one mistake. Huh? Just copy this. I will rectify it. Completed full. Next page. 1 minute. Huh? 1 minute. See, mistake. I'm just rectifying. Charge is in capital R. So 4 by 3 pi capital R cube. Capital R cube. Capital R cube. And this is R square. Rho R cube. Capital R square. So E will become rho capital R cube upon 3 epsilon naught into R square. Please copy this. Just rectify this. फिर on the surface वाला भी थोड़ा change कर देते हैं. On the surface, rho r cube 3 epsilon naught capital R square. So it will become rho r upon 3 epsilon naught. Change it like this. Graph of E versus R for non-conducting sphere. Important graph here. In this case, if point is inside, then we got E as rho r upon 3 epsilon naught. If point is inside, E inside. That means rho is constant, 3 constant, epsilon constant. What is relation between E and R? Direct or inverse?
Right.
Direct. So it will be a linear graph till it comes on the surface. Then inversely proportional to R square. So this is the nature of graph. If point is inside the solid non-conducting sphere and on the surface and outside. Copy. Done?
Yes.
Derive expression for intensity near charged cylinder. Using Gauss's theorem. Draw cylinder AB having radius capital R to be charged uniformly with positive charge having linear charge density lambda. Please copy this much. Then P be a point at a distance R near the charge cylinder. P be a point at a distance R from axis of charge cylinder near the charge cylinder from its axis. Draw a Gaussian cylinder CD having length L coaxial with cylinder AB of radius small r. It will pass through point P. Intensity at any point P is directed normally outward. Let ds bar be elemental area along P. Just draw the diagram.
Yes.
Okay. Consider a cylinder AB having radius capital R to be charged uniformly with linear charge density lambda. Linear charge density means charge per unit length. Linear charge density lambda. Let P be a point near cylinder at distance small r from its axis. Draw a Gaussian cylinder CD having height L, radius small r, coaxial with cylinder AB. Coaxial with cylinder AB. It will pass through point P. Just copy it in this.
So what does coaxial mean?
Same axis like concentric circle, coplanar. So same axis is called coaxial. Shall I clear this now?
Yes.
The electric field intensity E bar at any point P is directed normally outwards. Let ds bar be elemental area surrounding P. Therefore, by Gauss's law, flux phi is Q inside upon epsilon naught equals to E bar dot ds bar. Now Q inside is, see, lambda is charge per unit length. Q inside this Gaussian cylinder is only on the length L wala part you have to consider. So it is lambda into L upon epsilon naught, and E is constant ds cos 0 integration. Lambda L upon epsilon naught E into Gaussian cylinder curved surface area is 2 pi RL through which the field will pass. See, this is the cylinder, Gaussian one, So field will come like this outside. These are only curved surface area. So curved surface area is 2 pi r L. L you can cancel. So we get E equals to lambda upon 2 pi r epsilon naught. Now copy till end.
Yes, sir.
Okay. Done, na? Today we'll stop here. Next class I will take 15 minutes extra and next class 15 minutes extra. Hello, Veer.